Hey, what's up everybody? It's Ben from UFI University and we are back for the final round of Spintron testing on the Sorceress Pro Mod engine for Rod Chigfree's race car that's going to be out at hopefully this year at the Street Car Super Nationals, which would be really cool because that's where we first met and decided to start working on this thing. I'll just kind of catch you up a little bit on what's happened over the last year and a half or so as we've been working on this thing. You know, we started out where they were out racing at the track. They were having problems keeping the valve train together. My buddy Shane was working on the tuning stuff and came over and said, hey, come take a look at it. I walked over, introduced myself, you know, things just kind of led from there. We brought the engine here to Lake Havasu. We have lots of videos out there for you guys to go back and catch up on. Basically what we found is there was a lot of lacking in the stiffness of the system. We were losing control of the valve train, both on the intake side and on the exhaust side, where it was trying to push that exhaust valve open into a tremendous amount of cylinder pressure that gets generated in a 5,000 plus horsepower Pro Mod engine like this one. If you're not familiar with the Sorceress engine, this is sort of like a big block Chevy, right? It's a 5.3 bore space, all billet aluminum, big block Chevy configuration. Now think of that, a normal big block Chevy is 4,840, the distance from the center of one board to the next, so it limits the size of engine you can build. This is basically a stretched engine. Starting with that, we wanted to address the camshaft and the challenges that opening and closing the valve train has. When we first started our Spintron testing, you know, we're using a laser, we're tracking the valve motion and all that, and we could see right away things were not happening the way they were supposed to. There's a lot of bending, a lot of deflection in the system. At that time, we didn't have a lot of tools to work with. We decided to attack what we could work on, which was the profile of the camshaft. We wanted to basically open the valves more smoothly. Traditionally, the approach is if somebody sees that they're having valve bounce or controlling the valve when it goes to close on the seat and then it bounces and opens back up, traditionally the fix that most people do is throw more valve spring at it. We had this giant triple valve spring on the thing before, which had a tremendous amount of closing load to hold the valve shut on the seat. Now the only problem about that is the two things. One, that means there's a lot of load when you try to make that pushrod go up and the rocker arm tries to crush that valve spring closed. It makes everything in the system work harder, so you can get bending and deflection that way. One of the things we did is we took some spring pressure off of it. We did that by going from this large triple valve spring to this more appropriate double valve spring. On the surface, they don't look that much difference, but this one here is actually 40 grams lighter in total weight. Don't forget, the valve train has to be controlled by the spring, but even the spring's mass itself has to be controlled. So the lighter we can make that spring, the better off we're gonna be. That was step one. Step two was not having so much load that's trying to bend all the parts and stuff in the system. So instead of having 500 or 550 pounds of load on the seat, now we've only got about 400 pounds on the seat. That means less bending and deflection of the system. The next step was to build some camshaft profiles that were a little more gentle in how fast, the way that they try to open the valve. Of course, I reached out to my best buddy, Billy Godbold, and he designed a bunch of new load profiles. Then things got a little tricky because the Sorceress uses some giant camshafts in this thing, 65 millimeters, really large barrel diameters, kind of stuff that's not laying around everywhere that's hard to get a hold of. We reached out to LSM in Michigan. We asked them to make us some custom camshaft cores. They ended up making 5 9310 cores for us. We sent those over to Comp, and Billy Godbold and those guys back then ground up those new lobes he designed. We got those back and we started running them. Now at that point, we knew we still didn't have a very stiff valve train. Even then, we had dramatically improved the performance of the system. Just going from less valve spring and a better, more appropriate opening profile on the camshaft fixed, I would say, 75% of our problem. Then the real work had to begin. Traditionally, the rocker arms are bolted down to a stand and then the stand's bolted to the cylinder head. These are the old stands. Each rocker arm had an individual hold down stand. These are made out of steel and they're bolted to the cylinder head. Because of the arrangement of the head, you can see the stand here, it's got a cutout, and that was to clear the old head stud, which means we have 2 bolts on this side and nothing on this side. Well, what was happening is the tremendous amount of load that's put on the rocker arm when we're trying to open it was actually bending the bottom of this stand. In fact, if you look really closely, this one here, you can see it has a pretty good bend in it that's upwards. Well, these rocker arm shafts, they're extremely hard, so they don't like to bend, and they would snap. When that rocker arm snapped, game over. It would pitch it off, it'd come off the, you know, literally off the cylinder head and fall down in the rocker arm, and now you got a 7-cylinder engine. We would know that from the data log at the racetrack because at the same time that happened, suddenly the boost would jump up. That's because instead of having all that boost go into the manifold and 8 cylinders using it, now only 7 were using it. Unfortunately for us, having more boost in 7 cylinders still was not as much power as having less boost in all 8 cylinders. So we really needed to fix that problem. The way that we went about that is we ended up having to send the entire cylinder heads to Jessel in New Jersey. My buddy Grant Holcomb over there spent a tremendous amount of time redoing the configuration and re-engineering the whole setup. There just wasn't enough room to bolt everything down properly and have enough stiffness before. What he did is he actually machined the entire surface of the cylinder heads flat and just started over. Then he built a one-piece stand where all of the rocker arms are tied together. If you want to come over here and look, I'll kind of show you the difference. Instead of just having one single piece stand, now each stand is tied together on one plate that gets bolted down to the engine. There's huge amount of fasteners that hold the plate to the cylinder head, and then the bolts that hold the rocker arms down were also increased dramatically. Here's an example of the bolts that used to hold the rocker arms down. You compare that to what's on this thing now. The exhaust and the intakes have slightly different fasteners depending on what we could have. The other thing is, look at the difference in the diameter of the shaft. Instead of this one single bolt going through the rocker arm and just going into the stand, now there's a collet that goes around the rocker shaft that clamps it, and the stud that comes up through the stand and on the nut. We changed from an aluminum to a steel rocker, from an individual to a one-piece steel plate, used massive amount of fasteners, larger diameter shafts, used a collet to hold them down. We literally took every single trick in the book that we could get from Jessel and said, yes, do that. By the time we were done, we were talking about you could grab the rocker arm and pick up the whole car with this thing. Now it's so stiff. And the results have proven themselves on the Spintron. Now the last thing I want to show you is the increase in the push rods that we did. We called up our friends at Manton Pushrods, told them what we'd been doing and what we wanted. Here's an idea of the old pushrod that was in the engine. So this is interesting. If you look at this as the intake pushrod, normally a pretty high performance piece, not a bad piece, but because of the tremendous loads that were happening, I want you to notice all of the rubbing that was happening here. That's because the pushrod was bending and deflecting so much when it was trying to go up from the camshaft and push that rocker arm open. There was so much bending here, it's actually rubbing the inside of the cylinder head. We've replaced that pushrod with one from Manton like this, which is a much larger pushrod. We went from a 7/16 diameter all the way up to a 1/2 inch diameter pushrod here, which gives us way more stiffness in the pushrod. So remember, our camshaft is slightly more gentle opening, that reduces the forces. Our valve spring has 100 pounds less pressure, that reduces the forces. Our pushrod is much stiffer, which allows it to hold more forces. We've changed to the big one-piece rocker stand with the larger bolts, the larger shafts, steel versus aluminum. We've done everything we can to make the system more stiff. The exhaust is where the real problem was, because remember, no matter what we do with all that, we still have to push that exhaust valve open into the cylinder when we're on the power stroke. We're opening the exhaust valve around 90 degrees before bottom dead center on the power stroke. That means there's still a ton of cylinder pressure in there. And this thing has a very large exhaust valve. It's about 2 inches in diameter. You could do the math on how many PSI and how many square inches you have. It's a tremendous amount of force in addition to the valve spring force that you have to overcome. This is where we made probably the biggest change in the engine. We went from a 7/16 diameter exhaust pushrod to a 3/4 inch massive drive shaft looking pushrod here. And you can see them in the engine. They absolutely just astonish you when you look at how those fit in here. This is what it takes to get the stiffness that you need in a real Pro Mod engine. With all these changes, we went from them chucking parts off the engine every time they made a run when they would go above 7,800 to now we get to about 10,200 RPM before we even have a hint of starting to get out of control. So we're very excited to show you guys this. We're going to take you over to the Spintron and talk about some of the data and do a run. Okay, well now that we've done all this work to make the valve train better, one of the issues that crops up all the time is we're going to be capturing a lot more cylinder pressure than we were before. We just weren't able to use all of the potential of the engine that we had last time because the valve train was in such distress. It's not going to be surprising if we go from the 7,800 limit that we had before, that was, you know, basically put on us by the valve train, that now we can go to 8,500, 9,500, we can go over 10,000. In fairness, we may not have enough induction system to do that, but with the bigger turbos, you never know. My bet is the difference at the same boost level between 7,800 and 9,800, this thing will probably make somewhere in the neighborhood of almost another 1,000 horsepower than it used to make. Look for this car to go a lot faster. The problem is though, Now we got to be able to capture all that cylinder pressure and hold it together. So while it was down doing the valve train stuff over at Jessel, Rod reached out to our friends at ARP and said, look, we're gonna have to have some help keeping the heads on this thing, and we kind of need some custom fasteners, because before, remember, we had those individual rocker stands. Now we have the one-piece stand, and we got to kind of make sure all that clears. They went out and made custom one-of-a-kind various length studs just for this engine that came from ARP to Rod. His relationship with them has been ongoing for a long time, and he said, we want to make this the best it can be. So they came up with some brand new studs, new materials, new lengths, a lot more strong, and we're going to put them in that engine, turn the boost up, and make some runs. All right, so I want to take a little bit of time here and talk to you about what we did specifically with the camshaft. So we talked a little bit about how we had these new cores made, and so I wanted to show you what and why we needed to do that. Again, when it comes down to stiffness, everything matters. Even the camshaft matters. When they make a camshaft, the first thing you gotta do is select the right material. A typical, standard camshaft for a street car is gonna use something like 5150 cast iron. That's a really good material for a long-lasting, durable camshaft that's not gonna see a ton of loads and not a lot of stress. Unfortunately, though, what happens is when we get in there and we start abusing those camshafts, you can have failures pretty easily. So the stronger we can make the cam, the better off the rest of the valve train is going to be. Just for example, we changed the materials that we wanted to use for the Sorceress camshaft when LSM made our cores to a material called 9310, which is a much more resilient material. It's the same material that gets used in a top fuel car. The benefit of the 9310 is it's really, really good at taking a hit and coming back. It takes a sledgehammer every time it tries to force one of those valves open or close, and it doesn't crack or break. It's just a little more difficult to make that type of material. You'll notice the color of the camshafts first. Oftentimes when you see this copper color here, that's a masking that they put on before the hardening process. This technology is really old, like circa World War II kind of stuff, but what happens is we want the journal faces and the lobe faces to be really shiny, clean, and pretty hard, but with hardness, of course, comes brittleness, and you lose that sort of ductility to be able to be tough and take the abuse. By masking this off with the copper, it allows us to go through that heat treating and hardening process, and the barrel material isn't quite as hard as the face material. Here's an example of a camshaft that we cut in half and kind of polished up. That's a normal 5150 core here. And you can see where it's shiny. This is part of what they call the case hardening. The hardness happens from the outside in, and it only goes so deep. So you have to be careful how many times you regrind the base circle here so you don't get into the softer part of the camshaft there and cause a failure. When we were doing these camshafts, that was obviously a concern. And so the way that they do this is they start out with a straight shaft and they cut a spool from the linear dimensions. And that means they just go in with a lathe and they cut circles where each of the lobes and journals needs to be along the length of the block so that they line up properly with your lifter. Once you have your spool, you go ahead and mill, rather than with a lathe, they mill the shape of the lobes in the right firing order, approximately the right duration and lobe separation angles that the engine's gonna see. So that way when we do the final grinding process, you don't have to go so deep after the heat treating has already been done. This here is what we would call a UGL, an unground lobe. This is the linears have been cut, it's milled the lobes onto it, the heat treating is done and it's been straightened, but we haven't actually finished ground the lobes yet. So those 5 cores that we got from LSM, 3 of them are still in the UGL phase and 2 of them were profiles that Billy Godbold made and we had comp grind for us. One of those is what's in the Spintron engine right now that will go to the racetrack. When it gets finished, it'll have this more shiny look as our old one here. But one final difference I want you to notice, if you look carefully from our old camshafts to our new ones, is one huge difference we made was the size of the barrel. Let me grab some calipers for you. If we go here, we're at 1.2 barrel diameter on the old camshaft. If you go here, we're at 1.5. So we added a huge amount of barrel stiffness when we made the new camshafts. That's no small challenge though, because the lobes still have to have enough room so that when you grind the bottom of it, you're not below the barrel in there and have a weak spot. So they actually had to go in here, undercut these, and then deburr and polish everything. It takes a lot of effort for them to make a camshaft like this, but the end result is a huge amount of stiffness. Now, the last thing I want to show you here, just for comparison, just to kind of give you an idea of how massively overkill everything on Sorceress is I want to show you this camshaft, which is what's basically in the engine, as opposed to what you might be used to seeing, let's say, an aftermarket race camshaft for, say, an LS engine. So I got one right here, and I'll put that right next to it. That gives you some idea of just how massive the Sorceress Pro Mod engine is, and that's what it's going to take for us to go really fast on the racetrack. Before we start doing any real testing, we just kind of do a warm-up, and what that means is we get the engine spinning, we make sure that we have oil pressure, we listen for any funny noises, and we just kind of let it run for a while at a lower RPM, just like you would do if you're warming up your normal engine. Then what I like to do is just step it up incrementally in RPM. We started out at like 1,000, then we went 1,500, then 2,000, 2,500. Each time we're stopping for a few seconds, 35, 45, up to 5,000 RPM, and you can see we just sat there for a few seconds. Now the whole time I'm doing that, I'm listening to the engine, I'm watching the oil pressure, and I'm also watching the data. I'm looking for any problems in my valve trace. Is there any obvious problems with bending or reflection loft? Is there any bounce that shouldn't be there? At this RPM, we should have absolutely nothing, but we're just listening and watching and making sure. Now that it's warmed up, we can set it up and we can actually run an actual data collection test where we do some actual higher RPMs and we stop and analyze the data. We'll get prepped and set up and we'll do that. We're ready to do our test, and the way that I have it set up is somewhere between a drag race and an endurance test. If you remember way back when, this thing was clearly in distress already at about 7,500. On the track at 7,800, it would tend to spit the rocker arms off, and you definitely didn't want to go much above 8,000. We've significantly improved the system there now, so we're gonna do a pretty easy run here real quick. We're gonna hit the button, it's gonna start up and kind of like idle at about 1,000 RPM for a good, I don't know, 5, 6, 7, 8 seconds like that. Then it's gonna accelerate kind of like a dyno pull. We're gonna go all the way to 8,500 RPM, and then we're just gonna sit there for about 5 seconds or so, and we're gonna see what happens. So if you're ready, here we go. You ready? Yep, we're good, here we go. Okay, not too bad, right? So we'll stop and we'll check our data. We'll come right back. While Ross is in there going over and checking the health of the valve train, which we don't expect to have any problems with, we're gonna walk through and talk about a little bit of the data that we captured right there. Now, what's significant about that run that we just did is we accelerated up to 8,500 RPM, which was significantly more RPM than we could ever go to before without damaging stuff. More importantly, when we got to 8,500, we just kind of hung out there. In fact, it sat at 8,500 for 5 seconds, almost the entire length of the previous quarter-mile runs of the car. So normally you'd go zip, shift gears, you might see it for a 1/10 of a second. We literally sat there for 5 entire seconds at 8,500, like you're going down the backstretch at a circle track. But what we've done is we've taken this really kind of delicate flower drag race thing that was braking all the time, and now we've turned it into a semi-endurance race engine where you can just pin the thing to 8,500 and sit there. Now when we do more runs later, we're gonna go above 8,500, but I just wanted to show you just how stable all those changes have made the system. So take a look at some of our data here. This is the actual valve lift tree. It looks a lot like our cam lobe, where the valve's on the seat, it's opening, it reaches peak lift, it comes down, and it seats nicely. Now you may have heard people talk about things like valve bounce, and what that is when the valve comes down and it hits the seat so hard, it actually bounces back open. We don't want that to happen, obviously. Now there are some rules that we have, like a general guideline that we like to use is the stoplight kind of analogy, where if we have between 0 and maybe 10,000ths of an inch of valve bounce, we're gonna call that green light. It's not gonna hurt anything. The engine's moving so fast, you're probably not even gonna notice it. When we get upwards of about 15,000ths of valve bounce, then we're kind of like yellow light, caution. It's probably time to start paying attention here. By the time you get to 20,000ths of valve bounce, big trouble. We're gonna stop, red light, and take a break. If you look here, as we go up, what I'm gonna be watching is this is my valve bounce, and this blue line up here is a state, which will just give me basically a flag if there's any trouble. And you can see no flags anywhere in here. But as we go up, here's our maximum RPM. We get here, and we just sit there at 8,500 RPM for what seems like forever. And if I come down here, you can actually see it does have just the tiniest little bit of bounce right here. Roughly 3.75 thousandths of an inch, 3.8 thousandths of an inch. Very, very small amount of bounce. Not bad for just sitting there forever. You'll see that bounce will come and go as the RPMs go up, as it gets in and out of resonance. But if it gets a lot worse than that, let's say 10, 12, 15 thousandths, then we're gonna raise the flag and say, okay, that's enough. That's how we find our limit speed. In between doing each runs, we'll go through there and do normal maintenance, like we take the valve covers off, we check the valve lash, make sure we don't have any spring problems or anything like that, fix what we find or make changes, or if not, then we just keep on going and keep going until we find the limit. So we're gonna do that right now, and we'll come back and make another run for you when we're ready. One of the things that Ross is checking right now is the amount of valve lash between the rocker arm and the tip of the valve. Now this is a critical adjustment to any racing engine, and the right amount depends on your combination. Depending on how hot the engine's gonna get from when you start to when you're actually up to running, and the materials of the block. For example, this is a billet aluminum block with a billet aluminum head. It will have water in it, but what that means is when this thing gets hot, all those aluminum parts tend to grow. So you tend to gain valve lash. If you're not familiar with what lash is, you can see what Ross is doing. He's got feeler gauges, and he's checking how much clearance there is between the tip of the valve and the roller on the rocker arm, and that's called lash. What that does is it gives us a little bit of room for the engine to expand and contract and grow there. If the engine gets really cold, that gap shrinks up. If we're not careful, we don't have enough clearance there, that rocker arm will actually hold the valve open when the engine's cold. That's gonna make it pretty hard to start and run. You could burn the valves. You don't want that. On the flip side, if there's too much of a gap and the distance is really large, it can be harmful to the valve train. Let me explain. Typically that lash, here's my valve stem, and this is my rocker arm. So that lash that he's measuring with the feeler gauge is this gap between here. So if this gap is really large, when my push rod comes up and starts moving the rocker arm trying to open the valve, if there's a long way to go, then that means my rocker arm is going to get a good run at that valve and kind of smack it and pop that valve open. That tends to be really violent to the system and can really make the valve strings get out of control quickly. In fact, that opening violence contributes to a lot of that bounce we see on the closing side because the spring was never really in control of the system. Making sure that your lash stays consistent is a critical part of racing engine tuning. And so what we do is we make a run either here on the Spintron or on the dyno. We pop the covers off and we look, is there any broken springs or is there any extra parts? Did our lash change? If we gained a lot of lash, all of a sudden we have this huge clearance that we didn't have before, that means something in the engine got smaller. That's not good. So that's a critical thing that we're looking for, and typically we want to make sure that they didn't get tighter or looser beyond what we expected. So we're going to run through that now. Once all those are set, we'll stick the covers back on and we'll go hit it again. Okay, we made it through our other run where we kind of did the 8,500 RPM endurance, and frankly that was pretty easy. So we checked our valve lash and we kind of went over everything. Looks great. So now we're going to make a dyno pull style run. We're going to go up to 9250, which again is much higher than we were ever really safely able to go before. So same rules apply. We're going to do the run, we're going to listen and watch, we're going to stop and download the data, and we're going to go look at the engine and find out where we're at. So here we go. Something came off over there.
I blew a wall line.
Yeah, see that.
What the?
Wow. So we got just a little bit more bounce there. We're about 6.5 thou. Pretty happy with that. One little one right there. Let's see what that does here. Turn this off. There we go. A couple little bounces just right here. Tends to go right through them, about 11 thou. So we can play with that and kind of tune up the valve lash and play with whatever we need to play with there. We got a little oil leak over there we got to go fix first before we do another run, but we'll clean up the mess, come back and do some more. This one's for all the marbles. So we've done all of our due diligence and testing, and we've been sneaking our way up. We feel pretty confident. This time we're going to go all the way to the top. We're going to go to 10,000 RPM on this 640 cubic inch big block thing here. I'm going to hit the button. We're going to start recording. It's going to sit at what we consider idle speed here for around 10 seconds or so, and then we're going to accelerate upwards at about 900 RPMs per second. It'll take us around 9 to 10 seconds to get from 1,000 to 10,000 RPM. So hang on to your hats, and here we go. So we'll start our logger and we'll go. Right on, 10,000 RPM. That's pretty sweet. Wow. So you see as it goes through there, it has spots where the resonant, the energy in the system comes and goes. There's a couple of spots where you could kind of see a tiny little bit of bounce and it would go 100 or 200 RPMs past that. Totally fine again. The goal of Spintron is to find out where that limit speed is. Remember, we have like the stoplight thing, and so we're gonna come down here and take a look at when we're happy and when we're not. So we'll scroll over here. Just around 9,000, I got one tiny little bloop where it bounced our trigger, right? Remember, under 10,000, don't worry about it. Up to 15,000, then we're like, okay, let's pay attention. Well, that was 13 for one cycle. As we move above that, it goes right back down to around 10 or so. But remember, we're moving a giant 2.6 inch diameter intake valve, a very big, very heavy valve train. If you just look at this green line here, you can see what I mean by the energy coming and going. It sort of just hovers and kind of comes and goes, and each RPM's got a little signature. But notice after that bounce, that energy in the system goes right back away, and it's perfectly happy 95, 96, 97, over 10,000 RPM, all the way up to 10,027. It never has any trouble anywhere in there. And on the way back down, it has a little blip or so right about that same RPM, and just for a second. So what that means is you just don't hang out at 8,900 RPM and you're totally fine. You could be below it or you could be above it. You just don't want to park it there. With this car, that won't be a problem.
After each run, we like to check the valve lash, make sure nothing has moved around and we don't have any issues with springs or parts laying to the bottom of the cylinder head or anything like that. We just like to take a look.
Okay guys, so just for a comparison, I want to show you just how good that run was. I don't want to talk about whose data this is or anything like that because I don't want to make anybody look bad, and that's not really the point. The point was I want to show you what acceptable bounce looks like compared to not acceptable bounce. So a minute ago we showed you that we had 4 or 5 thousandths worth of bounce at 10,000 RPM on the Sorceress valve train. Well, I want to show you one that I pulled up from another set of testing we did. This was at 8,700 RPM. This is not the Sorceress engine. This is just a file that I'm showing you for demonstration. Remember, the Sorceress is up around 900 thou valve list and 10,000 RPM. So take a look at this one. That's at 767 valve lift, but the bounce is insanely crazy on this one. I'm gonna come down here and show you. It has a peak valve bounce of 54 thousandths of an inch. We're trying to stay under 15 thousandths. Not only that, look at how far the valve bounce is. It comes down here on the seat. We're at about 140 degrees when it bottoms out, and it bounces back off and comes all the way over here to 250 degrees. That's 110 degrees of bounce duration. It's almost like the bounce portion gets its own cam card. This would not run in your engine. First of all, it would break and destroy your parts. Second of all, it will not make any power. If you were on the dyno, you would see that power curve just go bleh like that. Think about, for example, from the piston at bottom dead center all the way to top dead center on our compression stroke, right? You have 180 degrees. Typically, we're not going to close the exhaust valve until 60 or 70 degrees after bottom dead center. So that means I've only got 110 degrees left before top dead center. We just saw the valve bounce for 110 degrees. Don't forget that it's on the compression stroke, so we typically light the spark plug 20 to 30 degrees before top dead center. So on something like this, this is how you would blow the intake manifold off of it. The intake valve is still open. They got fuel and air in the cylinder, and you light the spark plug, this thing launches the intake manifold off the car. This was another Spintron project we did for another company who came in and had this to start with, and of course we worked on it and we got it to look much better, much more like what we want. So again, let's compare this to the run that we just made with the Sorceress at 10,000 RPM. Here's 10,000 RPM, and you can see a dramatic difference. It almost doesn't even have any bounce here. And like I said, we typically will allow somewhere 10,000-ish, and so we're just under that at 8 to 9,000 there. The valve is way bigger. The engine is turning way faster, and we have way more valve spring pressure than that other engine I showed you. Again, that was just for comparison to show you what a little bounce looks like compared to a lot of valve bounce. So hopefully that's helpful. All right, everybody, this is the one we've all been waiting for. One of the things that we like to do before we wrap up a Spintron session is actually run the engine the way that it's going to be on the track. We've learned through a lot of our data collection that how the engine behaves on a dyno pull, where you just have this sort of smooth, controlled upwards RPM, and then you get to the top and you come back down, can be different than the way it is when you have these big, fast changes, or what we call transients, like, for example, when you make gear changes. Our Spintron is modified beyond what a stock Spintron is with a large resistor bank that we can shove energy into quickly. Otherwise, you can't pull the Spintron motor. It's an electric motor. You can't pull it down quickly, because if you do, it becomes a generator and it tries to push a bunch of extra voltage back into the drive system, and if it overloads the drive, it'll shut off. So most of the time, a Spintron can't do true gear shifting like what we're gonna show you. What we do is we take the data log from a run. So what we've done is we've taken a previous run from the Sorceress that went 580. We've input that run into our system. So what you're gonna see is we're gonna hit the start button. It's gonna come up and idle for just a second. And then just like you were up on the two-step at the Christmas tree, where they leave the starting line is about 4,300. So he's got his finger on the trans brake button. We're gonna be there at 6 seconds, and then we're gonna sit there for about 3/4 of a second. The Christmas tree comes down, the light turns green, and we let go of the button. The car will accelerate to about 8,800 RPM, where they typically make their gear change, come back to about 6,700. Second gear will go to 9,000, make the shift to 6,800, and we'll go out the back through the traps at 9,500 RPM. This is gonna be really cool if it works, and if it does, you're gonna get a good show. So here we go. Everybody ready? Start our logger, start our other logger, and we are ready. Here we go. And that's what it's like to go through the quarter mile on the Sorceress. So here you go, you come up, you're on the two-step, let's go the button, it ramps up, boom, there's, second gear, it runs out, boom, third gear, runs out the back. We made it to about 9,300 or so. And again, look down at the bottom, almost nothing in terms of valve bounce. We're really, really, really happy with the way this turned out. That was a 580 run through the quarter mile in the Sorceress on the Spintron. All right, well, that was a lot of fun. This has been a really long-term project in the works. Could not be any happier with the results. I know Rod wished he could be here today, but we just had to have fun without him. I think he's gonna really love how this project turns out. I realize that we haven't shown you guys everything we've done, and we just only have so much time for that. For example, we did not move the laser today and show you the work that we improved on the exhaust valve side, and that's for a couple of reasons. First of all, typically the exhaust is a lot smoother of an opening profile than the intake, and so if we can get the intake calmed down, we know we're going to be good with the exhaust. The exhaust has a lot less mass, so it's a lot lighter weight than the intake side. If it's lighter weight and you move it slower, and we have the same or greater stiffness, remember we have that giant pushrod on the exhaust side, the really nice rocker arms, we're very, very confident that the exhaust is in better control than our intake. But here's the thing about the exhaust. The exhaust has to try to open into the cylinder pressure. So on this 5,000 horsepower Pro Mod engine, there's a lot of cylinder pressure when that piston's going down on the power stroke, and we try to push that exhaust valve into that. Most of the bending and deflection occurs with a real running engine, which of course we can't simulate here on the Spintron. It would be nice if we could know what the cylinder pressure was rather than estimate. So we've got a plan for that too. When we get this engine all put back together and we're gonna go over and run it on the hub dyno and then of course on the racetrack, we've got ourselves a little bit of spicy package here that we're doing that has not been done yet in any Pro Mod engine that we know of. We actually have the ability to drill holes through the cylinder head and install some of these little sensors that are made by Kistler Corporation that actually measure the combustion pressure. Let me show you this little thing. These are really, really tiny little sensors. This sensor is 5mm by 0.5 thread pitch, and it's got little holes in there. This gets machined for a pocket that goes through the cylinder head into the combustion chamber, and it will allow us to measure the combustion pressures in real time, not just on the dyno, but actually while we go down the track. Once we have that, we know our valve train's good, so it will really help us with the engine tune-up, as the weather changes, as we change turbos, as we need to, we can work on our camshaft profile, induction, exhaust system. All the real answers for what we need come from knowing the combustion pressures. Between that and our EFI system and the data logging, we're pretty confident that Rod's gonna take this thing out and be able to go a lot faster than it went before. So stay tuned and we'll take you along for a ride on that too as we go to the dyno for the next phase of Sorceress testing. Well guys, we're about wrapped up here on the Spintron finally at EFI University, and since Rod couldn't be here to do all the hard work, he stayed home and sent Junior with him. He works at the race shop. These guys are gonna start tearing this thing down and get all the spare parts loaded in the truck, and they're headed straight back to Iowa, right?
Yep.
Before we know it, you're gonna have this thing in the car. We'll be on an airplane headed out that way to meet the team up up with Shane Tecklenburg, who's the tuner for the car. Who knows? We'll get this thing on the dyno and tune it up, and then we might even show up at the racetrack. But the goal is to make it go fast.
Very fast.
Everybody on this team has pulled their weight so far, from the guys at ARP making the head studs for us, from the guys at Jessel custom, building all this valve train, the guys at Manton doing the push rods, of course Ross and the guys here at AFA University that do all the hard work to make this happen, and then all your crew over there. A pretty successful outcome. I know it took a long time, but that's because good things take a long time. I'm super happy with the result.
Very happy.
Yeah, I hope you guys are, and you guys will get to see the end result of all this hard work in no time.
Amazing things.